Okay, so I'm back again for a second little lecture on VSEPR theory. This has to do with molecular geometry and how electrons are arranging themselves around atoms. Um, it might seem to you that it covers a very small array of atoms, but it covers a lot of things because when you get into giant molecules, each atom along a chain will still go into these same geometries. So I'll be talking about that right at the very end of this. Okay, so this has to do with covalent bonds. Um, so it really doesn't have to do with any metals at all in the periodic table. So like 80 of those atoms in the periodic table are metals, and so they're not really included in this stuff. Um, so if you look at what I've written up here, you have covalent bonds and VSEPR theory. We're going to talk about two odd molecules and their molecular geometries right now. They are the simplest molecular geometries. That's why we're covering them. A lot of people cover these first, but because they don't really follow standard chemistry, I chose to cover them second in this lecture. So if you recall, Be is an element in the second row that oftentimes doesn't have 8 electrons around it. So it's violating some of these simple principles of Lewis structures. And because of that, these molecules are pretty unstable. But if you look at the structure of this thing, so it's only got 16 electrons when you count them up using Lewis structure ideas, and it ends up creating a molecule that looks like this. So you have a central atom that only has 2 bonds, and it's only got 4 valence electrons. So that's going to be an unstable molecule, but they put it in this section on VSEPR theory all the time because it creates the simplest molecular geometry. So this molecular geometry is just going to be linear. And once again, that's because if you have 2 pairs of electrons around a central atom, so if we just choose this as our atom, if we have 2 pairs of electrons around it, for them to be as far apart as possible, they're just going to be 180 degrees separated from each other. So they'd approximately be where my fingertips are. And that would put the electron pairs as far apart as possible. And so the molecular geometry is linear because this pair right here is 180 degrees from that pair right there. And that minimizes the way those 2 pairs of electrons interact with each other. Um, so if you look at BF3, it's going to have some of the same kinds of issues. So in this particular geometry, you get this going on. And then each of these F's have 3 lone pairs. And so what makes this molecule strange is that the center atom only has 6 electrons around it. So it's also unstable. It's in row 2, so that's allowed. So Be and B are the 2 atoms in row 2 of the periodic table that have some issues sometimes with having 8 valence electrons, and their Lewis structures get odd. These are rather unstable molecules because generally, these things need to have 8 valence electrons to be stable. So this guy has only 3 bonds, and to minimize the repulsions, this thing's gonna so this molecular geometry is going to be trigonal planar. So what that means is if it's not easy to have models of this, but what that means if I had a central atom, it would be laying flat on the palm of my hand, and then all 3 of the other atoms sticking out from it would also be flat on my hand. So the whole molecule would just be flat, and it would look like this. This would be the B, and then these things, so the molecule would look like this, and these angles would be 120 degrees. So the electrons separate themselves here by 120 degrees, and it's a flat molecule when the electrons pairs are as far apart as possible, because that's what this VSEPR means. It means valence shell electron pair repulsion. So all of these geometries and all of these positions of these electron pairs, whether they're lone pairs or bonding pairs, are based on them minimizing repulsions by getting as far apart as possible. And so if you think back to our last lecture, so this is summed up in a giant chart on page 36. It has a lot of information in it. But you end up having a planar geometry, then a trigonal planar geometry, and that's, the planar, the linear geometry only comes when you have 4 electrons around the central atom, and that's a weird thing because you normally have 8 electrons around a central atom. And then this trigonal planar comes when you have 6 electrons around a central atom. So these are both weird things. And then in last lecture, I covered the 3 normal things where you have 8 electrons around the central atom. And in one case, methane, you had 4 bonds. So in that case, when you have this normal situation with 8 electrons around the central atom, the electrons are arranged in a tetrahedral arrangement no matter what. But if you have 4 things bonded, then the molecule is tetrahedral. But if you have 3 things bonded, but you have 4 pairs of electrons around the central atom, you then have trigonal pyramidal, which we talked about last time. And then if you have 4 electrons around the central atom, but you only have 2 bonds and 2 lone pairs, then you end up with water, which is bent V. So those 5 molecular geometries, which if I sum them up again, they go linear, trigonal planar, and then they go tetrahedral, trigonal pyramidal, and bent V. Those are the 5 common geometries in VSEPR theory. You can have more bonds to the central atom because, as you see, when you get to row 3, you sometimes can have 12 electrons around the central atom. Then things get a little more complicated. I'm not talking about that right now. I will talk about this one thing right as I end, and that's that you can think, oh, this molecular geometry only applies to small molecules. But if you make some great big organic molecule, like say this kind of thing, where you just start having all these C's linked together and you add all these H's. So this is like organic chemistry. You could draw a giant Lewis structure of all of this. Well, every one of these atoms has 8 electrons around it. Every one of these central C's. And so you can use this VSEPR theory to just look at a single atom here and kind of go, what's the geometry of it? And then you go like, what's the geometry of this? What's the geometry of this? And so you kind of do the chain by summing the individual geometries as you go along. And they will all follow this theory that we've just covered in these first 2 lectures. So this theory is a lot more powerful than you might think. Thank you.